a moment ago, I'm just going to show a couple of animations to re-summarize the different types of extracellular messengers that we talked about in Chapter 5. We talked about neurotransmitters coming from nerves, hormones coming from endocrine glands, and we also talked about paracrine signaling. And so I will just show these little videos so that you can see a molecule moving from one cell to another. So this is how one cell, for example, in this image we have actually four cells shown, and the way that they're going to communicate directly is by releasing a chemical, which we'll see between these two cells. So that yellow thing is the extracellular messenger. We added to that, we know that this one's hydrophilic because we can see its receptors at the target cell's membrane. Okay? So that's the release of neurotransmitter. We also learned that endocrine glands can release hydrophilic or lipophilic molecules out into the blood. It would be faster than that, right? But the difference is our hormones go into the blood, but they're still extracellular messengers. They still approach a target cell. They get just widely distributed. But the target cell is still going to need what? What is the target cell still going to need? Receptors. Okay. So our target cell here is yellow, the receptors are the red things, and the messenger are the purple things. And that interaction is the first message. What we added to it yesterday is that the target cell does something by opening or closing ion channels or activating a second messenger system. Or in this image makes a big yellow flashy flash. Again, that's not an option, a real option. Are you okay on those? Does that video help a little bit? Another type of messaging that we talked about was paracrine. So here we can still see a hydrophilic messenger, but it's not coming from a nerve, and it's not going into the blood, so it's not a hormone, it's not a neurotransmitter, but it still has the same type of binding, initiating a response. Does that make sense? All right. Let's get back into Chapter 7, where we were just reviewing the overlay of the nervous system and the rest of next week, what we're going to cover. And as I mentioned yesterday, Chapters 7 and 8 were really thrown at you in the Monday, Tuesday lab. That was covered this week. So we'll get back in there. We finished off our discussion yesterday about the different structures of the cell, the major structures. And in the handout that you completed over the weekend and you turned in yesterday was identifying that membrane of a nerve cell is not so plain. It has transporters and pumps and all kinds of other receptors and other products within it. Before I move on, what questions do you have about this general nerve cell structure? About the role of the dendrite, or we might still be confused on the role of the hillock, or the axon, or the terminals. Any questions at this point? Do all nerve cells look like that thing? Probably none of them actually look like that, but it's just an oversimplification. But even then, if we look at the general idea of a cell, not all nerve cells, all the billions of cells in your body aren't built exactly the same, but they have those general features about them that they conduct action potentials. An alternative image to the one which you labeled yesterday is in figure 7.2. Just does a better job at showing how one nerve cell can communicate with another nerve cell. It could have well just drawn another muscle cell or endocrine cell or hormone or I guess endocrine cell, or gland or something like that. But you can kind of see the basic repetition structure there. As I mentioned, some of the information that we'll study today will be repetitive. And so we now know, due to the lab that we did in advance, that nerves can deviate away from their resting membrane potential, which I have abbreviated with the term RMP, very quickly. And all it is due to regulating the ion movement across the cell. The key is it's regulated. Okay? The cell membrane is actively, and we also learned passively involved with making sure ions in the correct location. We know that ions are charged and can generate an electrical pulse if we move them from one area to another. I guess I just mentioned it is regulated. We talked about gated channels. We could also add in our leaky channels, the Cont. All these things are involved with ensuring where particular ions are or are not. The leaky channels we identified are always open, so as long as there is a gradient, the ions will be able to diffuse across the leaky channels. But the gated channels have to be open in order for an ion to move. So to verify that, what I try to drive home this point on this statement is if you look at your handout 2 that you just picked up, and if on the back, you notice that it had some of the gates that were closed. Some of you guys drew the ions moving through. What I wanted to illustrate is the gate's closed, ions can't go through there. So if you didn't draw it already yourself, I drew an arrow doubling back like road's closed, no passage through that channel. But through a leaky channel, sure, they could go through. So that's what I was kind of driving home with that activity. So just again repeating, our leaky channels or our open channels are always open. When an open channel is open, ions are able to diffuse which way? Down its gradient. If I'm not talking about a specific ion, I can't give it a specific fluid, but I can use the word down or passively transmitted. As well, we know that gated channels can change shape, conformationally change. That doesn't mean physically change shape or change what? Function. So, in the next bit of notes that we have is just going to reiterate what we learned in lab about the different types of gated channels and what they do. So, this will seem repetitive. And a review for what we learned on Monday. We learned that some of our gated ion channels are voltage gated, which open in response to a change in what? Maybe an action potential or just any other type of, what kind of stimulus? Electrical stimulus. So any electrical stimulus, and it doesn't have to be like an outside electrical stimulus. Maybe you want to clarify this. Ions can open voltage gated channels because ions carry charge. So maybe you want to write that in parentheses in your handout, that the voltage-gated channels, yes, they open in response to membrane potential, but honestly, that's because there's a change in ions, which are charged. So if there's a change in ions around the gated channels, they may be able to open or close a gated channel, a voltage-gated channel. In lab, the lab activity called them electrically gated. Electrical carries voltage, so I can use for voltage, but the two terms are synonymous in this description. As well as chemically gated channels can open when there's another chemical, like neurotransmitter or hormone, right? So you can put neurotransmitter, hormone, paracrine, ligand, extracellular messenger, right? If there's a chemical that thing is built to receive, it can open or close. So chemically gated ion channels open when there's a specific chemical that it receives. So this is basically a receptor like we learned in chapter 5. It's a receptor that functions as a gated channel. So acetylcholine gated channels will open when this neurotransmitter called acetylcholine is charged. And it's permeable to a specific ion. And we'll give some visuals of these in your handouts. Okay, the voltage gated and the chemically gated. Other types of gated channels include mechanically gated ion channels. And these open when there's some type of physical stimulus. So all these are opening in response to stimuli. Mechanically gated channels open when there's a physical stimulus. We'll see these, we'll put these in use when we look at the blood pressure, how our body monitors blood pressure. So pressure physically changes the state of some of these receptors. But your ability to, you know how you can hear, you've got the ability to hear mechanically, sound vibrations push on receptors in your ears, which changes the ion permeability at which nerve? What nerve allows us to hear? Cochlear nerve, right? So mechanically, sound waves push these receptors out, allow you to detect sound waves. But probably, in addition to like blood pressure, we'll use more of these, like your sense of touch. You can probably appreciate that better, right? You could feel something on your body. It's because you're activating mechanically gated ion channels at specific cells. There's also thermally gated receptors, and they open in response to different modes of temperature. If you remember from your general biology classes, you know that temperature can affect how a protein is built. And so as temperature changes, some proteins change shape. And so some are more sensitive to warmer environments, and some are more sensitive to cooler environments. So it gives us a range of temperature that we can detect. Say, I can tell when it's minus 28 in the winter in Oklahoma, okay, or like it's going to be this weekend, like 98 degrees. But I can detect those ranges because I have thermoreceptors in my body. And they're just designed for picking up these different modes of stimuli, and they just let ions move across the cell at which they're expressed. This is just repeating what we know from lab. When a gate is open, ions are going to move quickly, and maybe instead of using the word, we can say what? Yes, they're moving, but really they are diffusing really quickly across the membrane, along or you could say along or down. We've been using the word chemical concentration gradient, but really also their electrical gradient. Explain momentarily. So it's not just a concentration gradient. We're going to unfold electrical influences as well. And when ions move, we have an idea that voltage is true as well. So it does actually generate a true electrical voltage across the cell membrane, right between the extracellular fluid and the intracellular fluid. And just a local change in voltage. Visually, this will help maybe better than what you drew in handout number 2 or what I drew in lab this week. But for example, the voltage-gated sodium channel. It's going to be physically closed when the internal environment is negative, or in other words, when the cell's at what? At rest. Okay? When the nerve cell's at rest, the voltage-gated sodium channel's closed. Other channels, like leaky channels, may be open, right? But this one is closed. Okay? So through that channel, sodium cannot enter, just like the channel you drew or labeled in handout number 2, right? It's closed. There's no entry through that passageway. When some other stimulus causes that internal environment to depolarize or become slightly less negative, changes the shape of that gated channel, and it begins to open. And now sodium can diffuse down its electrochemical gradient. And we now know that's which way? Into a nerve cell. Very good. And sodium would diffuse into a nerve cell. You can see this oversimplified in this image. The voltage-gated sodium channel is the purple thing. The extracellular fluid is blue. The intracellular fluid is tan. And we can see an implication of rest by the negative values in the far left scenario. And then we can see the gates, right? We can see sodium's not entering. However, when some other factor causes the internal environment to become less negative or locally positively charged, it opens and sodium flows down or diffuses down its concentration gradient. Is this repetitive or okay? We feel like we can move on, right? All right. I just want to make sure. Sometimes this lecture comes ahead of the the lab, so fine line to walk. Other voltage-gated channels we'll use this semester include potassium and calcium gated channels. The potassium at the nerve is concentrated at the axon and also the hillock. Calcium you'll find in greater concentration at the nerve axon terminal, which has something to do with what? Not at the terminal, the release of the neurotransmitter, but we'll also see it in our skeletal muscles and our other muscles as well. But right now at the nervous system, the voltage-gated channels are concentrated at the voltage-gated calcium channels are at the axon terminal. Since we're doing okay on the gated channels, I'll quickly go through the chemically gated channel example. Same scenario. When the stimulus is absent, the gate is closed. When it's present, it's open. And so you'll notice that there's a sodium-potassium chemically gated channel. It's permeable to not only sodium but also potassium. These ions would move which way? Down their own gradients. The sodium would move direction it would move into, and potassium would move out, okay, through this chemically gated channel. Right. So same thing, gate's closed, no entry or exit. Only when, say, neurotransmitter, extracellular messengers are present, then the gate opens and allows for net diffusion of each of the ions. We can see this summarized in the image to the right on your handout. Same thing. Stimulus absent, gate is closed, stimulus present, gate is open. So up till now, like the first unit, we would have just called this a receptor. It's receiving a specific molecule. But we know the receptor can open or close the channel. But I could have gone through the same thing with a thermally and other mechanically gated channel as well. Any questions before we move on? Structurally, when you go into anatomy, you'll look at the structural differences of the nerve cells in better detail. I'm not going to hold you accountable for anatomically the different types of nerve cells, but I want you to understand the structures, the general structures like we studied before. But I just want to present it to you because it is important to understand that there are some differently built nerve cells, and they're in different parts of our body, and they function differently. Anatomically, some are called bipolar, pseudo-unipolar, or multipolar. The ones that we've described so far are multipolar. And I don't want you to confuse the term bipolar with the disease, because even though we're in the brain, bipolar just means what? Two. Okay? And so it's just anatomically, looks like there's two ends. One looks like it has another. And so if we look at them, on the far right is what we've described so far, a multipolar looking nerve cell. But there's some variations about where the cell body is located. If the cell body is located kind of, if all the dendrites are peripheral and then there's the cell body, then the axon, that's called bipolar. So it looks like it has two ends. The dendrites look like the terminal, so you kind of got to pay attention as far as where that nerve cell is and the direction which it's signaling. As well as the pseudo-unipolar. These are unique in that the dendrites extend to directly the axon, and the cell body is kind of displaced, and the axon continues to the terminals. This, if you were in lab yesterday, is the type of cell that we studied in the spinal cord. So if you're coming in the lab today, remember how the cell body is kind of projected off. Do y'all remember the ganglia, the spinal nerves? Okay, so those are what we saw, what implied were there at that little ganglia of the spinal cord. Structural is important, but we're here to study the functional component. And so if we look at our nerves functionally, they actually fit into that neat little homeostatic box that we started out the semester with. And so some nerves are collectively called afferent, and they provide for detection of stimuli, and they're connected to receptors, and some type of specialized receptor out in the periphery of the body. And so afferent nerves, we learned from our introduction, are out in the peripheral nervous system detecting stimuli. They communicate with cells that are in the central nervous system, brain and spinal cord, which are collectively called interneurons. Inter means what? Between. So these are the cells between the afferent and the efferent. They're in the central nervous system. So really they are the control center, the integration center, the interneurons. The interneurons are the sensory information receiving, efferent command, output controlling, set point comparing cells. Okay? They're found in the spinal cord, they're found in the brain. They must then, if they're going to control effector organs, they've got to have a nerve cell that they communicate with. And those cells are called the efferent neurons. Efferent neurons are those nerve cells that conduct away from the brain or spinal cord to what type of cell? Yes. And that target cell would work as the what in the homeostatic pathway? It would work as the effector. And so our afferent nerves and our efferent nerves are in the peripheral nervous system. Our interneurons are in the central nervous system. So the efferent nerves extend out, abbreviated here in S for peripheral nervous system. Afferent nerves actually start out in the peripheral nervous system, but the interneurons, they make up the brain and the spinal cord, so they're safe, if you will, housed inside of those structures. This can be summarized with figure 7.6, and honestly, it can tie right back into that overlay of the nervous system that we started out with in chapter 7. And so if we look at, again, in the light yellow versus the brown area, the central versus the peripheral nervous system, our sensory nerves, their dendrites, would be out somewhere in the body. Okay, it's picking up stimulus. Like say if you're feeling something in your fingertips, the dendrite region of your sensory nerves starts there. So the cell bodies are maybe over there, actually. Or the pseudo-unipolar. But anyway, we'll keep it simple for right now. The dendrites are out there picking up the stimulus. They would generate action potentials towards the spinal cord. And so their axon terminals are where? In the spinal cord, in the central nervous system. And they would release neurotransmitter on cells and other nerve cells on their receiving end. What part of the interneurons can receive neurotransmitter or chemical messengers? What part of the cell? The what? The dendrites. The cell body, right? And then they can generate action potentials and release neurotransmitter on other cells on their parts of their what? On their cell bodies or dendrites. So they can generate action potentials and release neurotransmitter on some other cells. So it's just a loop of communication, if you will. But our nerve cells are built to receive and communicate on a specific direction. Does that make sense? Can you see in this image how the interneurons, what color are they? Green. The green cells are the interneurons. And notice the entire cell none of the cell exits the central nervous system. Only our afferent and efferent nerves extend into or start and exit from. But you won't find the afferent and efferent nerves completely in the central nervous system. These are part of which nervous system? The peripheral nervous system. Before I move on though, can you see the directionality? Afferent signals into the central nervous system. Interneurons process that, and if necessary, they can select an appropriate output or efferent neuron. So we'll see this relationship over and over. Before we can look at how these cells work, we just need to look at a nerve cell in general. And then in chapter 9, central nervous system, chapter 10, sensory input, chapter 11, motor output. And so in order to understand a nerve, we need to understand the resting membrane potential, which we covered, I think, in really good detail on Monday. So we'll just repeat it, and I'll work decently at a fast pace unless you need me to slow down. and we need to ask specific questions. But we're going to review the role of the resting membrane potential, and this is what you were addressing in handout number 2, the resting membrane potential. And a lot of you guys on your handouts, and I didn't mark you off because I didn't really lead you in that right direction in that last question, but on the last question it said explain your plot for your resting membrane potential. Might want to go back and review. Our add is due to the sodium potassium pump and the leaky channels and the gradients. You might want to add more detail so you better understand that. We do know that a nerve cell does maintain resting membrane potential. Before we can understand the resting membrane potential, we just need to understand what the word membrane potential means. Okay? And so it's due to the movement of ions that move along their chemical and electrical gradient. When we're in Unit 1, we just talked about chemical gradient for passive versus active transport. And then I said we'll get into electrical chemical gradient, so we're here now. And we need to take into the dual consideration, or dual pools, influences of not only the chemical drive, I guess, for a molecule to move from one location to another, but we have to take into consideration any electrical attractions that a charged particle may have upon itself. Okay, so collectively, you can call that the electrochemical gradient, taking into consideration both electrical and chemical draw. If across a membrane between the extracellular fluid and the intracellular fluid, or wherever, if there is a charge, so in other words, the fluids are not neutral, if there is a charge, there is what's called the membrane potential. You've used the word potential, it's the ability to do work, right? Potential ability to do work. And here it's across the membrane. If there's potential, we could do electrical work across the membrane. You okay so far? All right, figure 4.3 is where this is probably illustrated better. In panel A, you can see that positively charged particles are attracted to areas that are what? Negatively charged, and vice versa. I'm going to come back to this image and kind of fill in the text a little bit. We already identified the membrane potential as being a difference of electrical charges, or in other words, a difference in anions or cations or ions. If they aren't equivalent between the two fluids, then there's going to be a separation of electrical charges. We also know that oppositely charged particles attract one another, like we just illustrated in the previous image. In order to have a difference, the cell will actually create the difference. Okay, so we already know this. It takes energy to actually create the gradient. But like we saw in the first unit, the whole point is where we're going is first we're going to create the gradient, and over the next day or two we're going to do what with it. We create it so that we can use it. So it does create energy to generate that electrical force. And in this case, we're going to measure it in millivolts. That potential is measured in millivoltage. Some cells can quickly change that voltage, like we see in nerve cells, but we're going to see it as well in Unit 3 with all of our muscle cells. All muscle cells also have the ability to do this, so it's imperative that we get a good command of these voltage terms, not only just to understand the nervous system, but really the rest of the body. We generate electrical impulses. And when there is no change in electrical voltage, it's called the resting membrane potential. And it looks like the next line below there is a redundancy, so you can omit that line just below it, and where it's repetitive. Do it. Okay, very good. Thank you. Didn't catch that one before. Or we make the corrections in the handout. what's causing this. We know it's our ions. Some important ions that we'll see include sodium and potassium between the intracellular fluid and the extracellular fluid. Again, redundant. Yep. Because of lab on Monday, we know that sodium is a greater concentration in the extracellular fluid as well as potassium in the intracellular fluid. In the handout it says it's due to what? Due to what? Somebody fill in. Very good. The sodium-potassium pump is our active transporter. And the next bit is the what? The leaky channel. Yep. You might want to just add in there the term leaky. The next bit is going to add a little bit of detail. It's going to kind of drag it out. So I'm sorry it's so entertaining. But I want to, we've just been stating these things, and now we're going to understand it in a little bit better detail as to the why. And so a better way to understand it is to look at each ion individually and to identify each ion's electrochemical gradient. So that if we understand them individually, then maybe we can look at the collective influences. So we're going to look at potassium first and sodium, realizing you wouldn't find just one ion or the other in a cell, but we're just going to isolate them to determine the electrochemical gradient and draw for each of those. Now, we have an idea. We know that potassium, because of the pump, is in greater concentration inside of the cell, right? So chemically, we can handle it. Chemically, it wants to diffuse, we know, where? Out of the cell. Okay? So through those leaky channels, it wants to leak out. But pumping is going to get pumped in. So we can handle that. It's going to passively diffuse out of the cell. Or in other words, down its concentration gradient. But now we're adding a level of influence here. What is the charge on potassium? It's positively charged. And so it's going to be attracted to things that are what? Negatively charged. And so what happens is, because it's positively charged and it's attracted to things that are negatively charged, and because it's actively pumped into the inside of the cell in high concentration, it's naturally just going to be attracted to things that are inside of the cell. So electrically, where is it drawn? Which way? No? Electrically, it's drawn where? Where does it want to stay? It wants to stay inside. Electrically, but chemically it's drawn out. Okay? So it has this flow out, electrically stay in. So you ever been like that, drawn in two directions, right? And so we got to see, well, what is the net pull? Is it more drawn, right? What's the draw on it? And because it's charged, what influence does it have on the internal charge of the cell? Because it chemically wants to diffuse out, electrically it wants to stay inside of the cell. And so this is summarized here. My brackets stand for the concentration of potassium. It wants to draw it out, but electrically attracted in. So that's just repeating what we mentioned. And this electrochemical gradient of potassium is like the contributor to our resting membrane potential. It's the biggest influencer. Yes? Yeah, so good question. The question that she had was, well, what is it inside of the cell that's negative that allowing potassium to attract to it? Good question. What do you think's in there? There are some other ions, definitely. What else is in our cells? It might have a negative charge or might be water soluble. There's definitely fluid in there, and there's also a lot of proteins. A lot of our proteins that are inside of the cell, say your microtubules, you name it, enzymes, whatever, allowing them to be hydrophilic. So we've got all these charged proteins, the potassium attracted to it. It's a great question. And so because those proteins are saying, potassium stay, right? And the gradient saying, you go, right? Come on out. The internal charge of a cell, if potassium were working alone, would be about minus 90 millivolts. That seems comfortable, right? That's really close to what we've seen before. Of what? Minus 70 rest when sodium's in play. Okay, so if potassium were doing its thing by itself, the inside of a cell would actually be even more negative than if there's sodium present. Okay? So let's look at the electrochemical gradient for for sodium. It too has a charge, it too has a gradient. You know chemically it wants to diffuse where? Into the cell. It wants to diffuse down its concentration gradient. It's also positively charged, so it wants to be attracted to other things that are negatively charged. And the same just where you are kind of influence plays on sodium. Sodium's in greater concentration outside, so it's electrically going to form bonds with things that are where? Outside of the cell. So electrically, sodium's attracted outside. So it has this opposite type of push-pull on it as well. The question is, well then what would this charge of a cell if it just had sodium only? Look at this. If a cell had only sodium and allowed for it to reach equilibrium, the inside of the cell would not even be negative at all. It would be positive 60 millivolts. That's way away from what we see in a normal resting cell. Sorry. And so what happens is the collective work between the electrochemical gradient for potassium, the electrochemical gradient for sodium, the pump doing its thing, we know that the collective effect is a cell has a membrane potential of about minus 70. Sorry. The cell has a really negative internal environment of about minus 70, close to which ion by itself, closest to potassium. And so this tells us is sodium and potassium don't diffuse at the same rate. Which one diffuses more? Potassium, actually, because it's closer to this. So the resting membrane potential of most cells, the value we'll use, minus 70, but it's a range, right? It's not exactly minus 70 for every billions of cells. But it's about minus 65 to minus 85 millivolts. And I'm going to go to the second bullet down, or the first one, excuse me. The resting membrane potential is most influenced by potassium. And the membrane is just more permeable to potassium than it is to sodium. If a membrane was equivalently permeable to sodium and potassium, the membrane voltage would be the average of minus 90 and plus 60. So the value would be what? Plus 60, minus 90, about negative 30. Was it 15 actually divided by 2? Closer to 0, right? Than really negative. So potassium is going to have the greatest influence. So the next image, I believe is actually from your text, but just summarizes the role of the pump, the role of the leaky channels, and the electrochemical gradients, allowing for a cell to have a rest of about minus 70 millivolts. And a big statement is if we're using the word resting membrane potential, what does that word imply? So let's use something besides the word rest. What does the word resting membrane potential mean? No signal, no stimulus. It has a charge of minus 70, maintaining a charge that's not receiving a stimulus. I think sometimes the word rest is kind of a bad implication, like the nerve's taking a nap and not doing anything. but your nerve is busy, right? Just to keep resting membrane potential, it's driving that pump, spending energy. And so it's actively involved in creating that resting membrane potential. But the term simply implies that it's not yet received a stimulus at that moment in time. And so what happens is the nerve cell can deviate away from resting membrane potential. And some terms that we're going to use include an action potential, we'll cover in Chapter 8. Also, a gradient potential we'll cover between Chapter 7 and 8. I can't remember exactly. I think Chapter 8. And then when we get into, say, the sensory division, we'll get specific to different types of gradient potential called a receptor potential. So you might want to make reference to 7.1 to help review the different types of potential charges that a nerve cell may undergo at any given time. So a little review. We know that sodium leaks, potassium leaks, and the pump creates those gradients to allow for a cell to maintain an internal charge of about minus 70 millivolts. Any questions before we move on? Right, so that's resting membrane potential, and we cover that in handout number 2. And in handout number 3 that you're going to turn in next Tuesday is going to deal with an action potential. So we're going to start to apply also some information that we learned in lab Monday and Tuesday. And so nerve cells and other cells can generate electrical signals or action potentials to allow for communication by just regulating additional movement of ions across the cell. In addition to action potential, there are these things called gradient potentials, which also are addressed in handout number 3. And it's always one of those which came first, the chicken or the egg kind of discussions. I'm going to talk about the chicken first and then come back to the egg. I'm going to talk about the action potential first and then come back to the gradient potential. But, I could just as well talk about a gradient potential and an action potential. And your book, I think, goes in that format. That's just well logical. But generally, I put the action potential up front because we're getting into the lab about now, typically. And so it correlates with the lab that we're getting into. But, so you're very familiar with an action potential, at least have a nice introduction to it. And you have an idea of the complexity of an action potential. However, in order for an action potential to get initiated, there first must be a subsequent, or not subsequent, but an initial gradient potential. So we'll come back, I'll define each, go into better detail of the action potential, and then probably on Monday, I don't think we'll get there, we'll put into practice of what the heck a gradient potential is for. Just to review some terminology that you guys became familiar with from your pre-lab, number 3, I think it was, the nervous system. We can talk about polarization, any charge other than 0 millivolts, so whether it be positive or negative, the membrane may be polarized. We also identified the term depolarization. And this is a little catchy, but I think it'll be easier if you use the term less negative instead of the term positive. Because a nerve cell's at rest, very negative, right? It can depolarize, say 2 millivolts, but it's still not what? It's still not positive. So try to train your brain, even though it is moving in a positive fashion, just say less negative to describe depolarization. The cell depolarizes, it becomes less negative than it was at resting membrane potential. We also know that membranes can repolarize, return back to resting membrane potential, so gaining negativity. We also know that membranes can hyperpolarize and become even more negative than at rest. Become real familiar and be able to use those terms. Not only in the nervous system, but all of our muscles. We use these terms. So So let's just give a quick definition and kind of a teaser into what a graded potential is. It's a local change, it's a deviation away from resting membrane potential. But it's described as in grade and not very long lasting. And here's the key right here. Maybe this is where you want to put your star or circle or whatever. It's changes in potentials, but they occur where? Under the threshold. So they never cross thresholds. So it's very much different from an active potential. So deviation away from rest, but it doesn't approach threshold. Okay? So therefore it's not going to be an action potential. As well, the length of a graded potential is determined will be determined as far as how long that particular stimulus is present. If something's there for 2 milliseconds, graded potential will last for 2 milliseconds. If it's there for 5 milliseconds, it'll last for 5 milliseconds. So the bigger the stimulus, the more gates open, the greater, right, the response. But it's still below what? Threshold. So in a particular nerve cell, it can have a graded potential if it changes polarity but doesn't cross threshold. Here's the deal with our graded potentials is because they're kind of like anatomically in a tiny little microscopic spot, if you move physically further away from that spot, the rest of the cell may not even know that there's a stimulus present. Because that stimulus is so weak that it doesn't let enough sodium into the cell. The rest of the cell, voltage channels, they don't even know. Right? They're there at minus 70 and just at rest. And so if a graded potential is not changing, I guess, their membrane, as soon as that stimulus is gone, that cell, that part of the membrane is going to go right back to what? Rest. Okay. So up to this point, the graded potentials really look useless. And so they are useful, but we won't make the connection probably until Monday. But if we look at this image, we can see just a cross-section. This could be a dendrite of a cell in your brain. Okay? We can see in the first panel, it's at rest of about minus 70 millivolts. When some very weak stimulus, chemical, whatever, is present, that tiny little section of membrane undergoes a potential change. It deviates away from rest, but it's not enough to open up gates in the rest of the membrane. So the rest of the membrane stays at what? Rest. And as soon as that change happens, that membrane goes right back to rest. So all it is just a quick local change of potential within a nerve cell. Here's the deal, though. This image is just trying to illustrate what I mentioned earlier. The further you physically get away from that weak stimulus, rest of the cells at rest, no acknowledgement. You see how the arrows are dissipating weaker and voltage change. Our graded potentials may not only, we'll learn depolarize, but here's the new bit that we're going to add to it, is some may actually hyperpolarize. We'll come there in just a second. This image, the Sabin magnitude varies, and hence the term graded. Not all of our graded potentials, say, maybe go up 2 millivolts, 3 millivolts, 5 millivolts, whatever. One may go 2, one may go 5, one may go 7. One may go 10 millivolts. It just depends on the amount of stimulus. However, in a graded potential, we may not just have depolarizations like maybe you've been implying since Monday or Tuesday from lab, but actually here's where we'll make a connection. Some are hyperpolarizing and moving further away from threshold. Yes, you're right. Yes, away from resting, but really more away from threshold. Okay, so we'll make the connection of these, what they're useful for. That's the teaser. Okay? Graded potentials depolarize or hyperpolarize, but the change is below threshold. So I'm going to leave you hanging there, if you will, and then we're going to conclude the rest of today's presentation with just reviewing an action potential and the events in that. So our action potentials, I tend to abbreviate these APs, and you can use that abbreviation as well, as long as it's used correctly and in context. And what happens during an action potential is, yes, there is a deviation away from resting membrane potential, but it's quick. Okay? And it's about 100 millivolt change in total potential charge. So if we're minus 70, it actually changed to about what? Like 100, about positive 30 millivolts. Okay? Those are the textbook values. We know that each cell would have an actual voltage. And so as we learned, our excitable tissues, muscles and nerves, do this. These do not weaken when compared to gradient potentials. So an action potential, once it's generated, we'll learn it triggers an action potential in the rest of the cell, and it just continues. They have the same kind of force, still full amplitude of change. And this is how our nerves communicate. So maybe you've not used the word action potential before, but maybe you've used the word nerve impulse before. We talked about nerves before today. A couple of people. Okay. And so what happens is it may initiate at the cell body, but definitely at the hillock and be conducted. It's conducted right, along the axon and eventually to the terminal. And so what we'll do today is review those events along the axon. We may or may not get to the events at the terminal yet. Zoom in, if you will, the event. And I gave you the alternative term as well. You can also call it a nerve impulse. Oh, look. Page 7. What do you think I'm going to have you do? Draw. All right. Why don't you draw an action potential? Be sure to title it as such. You're going to label this an action potential. What is on your y-axis? Millivoltage. On the x-axis is your time in milliseconds. Just plot an action potential. Plot and label an action potential, like you did in lab, starting it at rest, and then plot the rest of the action potential. And then somewhere on there lightly, maybe you put a pencil or whatever, illustrate where that nerve cell's threshold is. So plotting and labeling an action potential. All right. This is just a screen capture from the PhysioX program, so ignore the scale on the left. I put this together years ago and I've never fixed it, so I'm going to give you a heads up. The scale is off. The scale that you guys that I've seen on your handouts look accurate, okay, as far as the voltage is concerned. We know that when a cell is maintaining its resting membrane potential that we painfully walk through for about 40 minutes, okay, the pump and the leaky channel, the electrochemical gradients, that's happening. At some point, as illustrated by the blue line, some mode of stimulus is received, whether it be chemical, mechanical, thermal, electrical, whatever. If a cell is going to be excited, it will do what? It'll depolarize. Okay? And if it depolarizes beyond its what? Threshold, then voltage-gated, which ion? Sodium channels will open up, probably at the hillock. So letting which ion in during this phase? Sodium moves in for depolarization. So during this upward tick and the continuation of depolarization, initially some type of gated sodium channel opens, and then the voltage-gated sodium channels open. Sodium just floods down its concentration gradient. We reverse the polarity from really negative to positive fast, and then those gated channels shut. Okay. Then we change the polarity, so what happens next? The phase is called repolarization, and what physically is happening? voltage-gated potassium channel is open, and potassium is exposed to its electrochemical gradient. So we know that it diffuses more out of the cell, causing the cell to regain its polarity. I'm not as sure if I explained them both or just one lab. What happens is those voltage-gated potassium channels are slow. So even though the resting membrane potential is met, the gates are still open and potassium continues to flow out. And so we can have a phase of what? Hyperpolarization. I don't have time today to explain it, but there's a reason for this. Okay? It's not an accident. Okay? It was like a mal-design or something like that. There's a reason for this, so we'll come back to why that is. But at some point, the voltage-gated potassium channels will close. The pump is pumping. The leaky channels are leaking. Okay? There's a song I want to create. So if anybody's artistic, I'd love your. I am not artistic. Y'all remember the show Earl? Doctor said I'm mildly artistic, so I might like that. I'm mildly artistic. Okay, artistic. Okay. So I'm not mildly artistic. Okay. So, but if you are a little bit artistic, have some songwriting ability, I'd like to create a song, like really a rap, like so with me. I can't rap, but the pump is pumping, the leaky channels, right? That's going on all the time. Anybody? I need your help. But got the template going. But so that's happening all the time, in addition to the voltage-gated channels doing their thing. So the pump is pumping, the leaky channels are leaking, the cell goes back to resting membrane potential. Okay, very good. The question is, this is summarized, these events are summarized for you in table 7.3, reviewing which channels are doing what during each phase. And so during rest, we know that our gated channels are closed, like we did in that handout number 2, but the pump's pumping and the leaky channels are leaking. Okay. At some point, depolarization is going to happen through some type of gated channel, letting sodium in. But notice the potassium channels are closed. But repolarization, we switch, where our sodium channels closed and our potassium channels open. And then we've got to go back to resting, where our potassium channels are closing and the sodium channels are also closing. Summarized in table 7.3. Which can be summarized in this little animation. The action potential is going to be illustrated by a yellow flash, which we know that you can't see it in a nerve cell, but then it'll zoom in and show the different ions, and you can see how they can flux between one location to another. So it does a decent job illustrating how an action potential is conducted. Let me take these labels off. So here's the deal. Right now we're at the nerve axon. We're conducting an action potential. Chapter 8, we're going to jump back and say, well, how did that happen? That's where we're going to make the chicken and the egg, right, basically. So we're presuming something has happened, and now we're conducting an action potential. What's happening is those channels, like we saw in handout number 2, are going to switch between open and closed, and we know the electrochemical gradient. In the far right, in the green, is representing the sodium-potassium pump. And I believe the purple is sodium and the blue the potassium. So we can see an internal charge. It's negative inside and more positive on the outside. The membrane has potential. Yeah, so sodium in purple, we can see the gradient. We know that sodium diffuses down, potassium diffuses down to the respective fluids. Try to reach equilibrium. This is going to plot ion movements as well as an action action potential. So when sodium moves in, the cell depolarizes. That's fast. Sodium moves in, the cell will depolarize. Potassium moves out, the cell repolarizes and hyperpolarizes. And then the pump will do its thing, and the cell will get back to rest. The rest of the image does a little better visual job. You can see actual implied ions in which they move. Voltage gated sodium channel is open, and sodium's moving where? Into the cell. And watch this. Just look, physically, these positively charged things are adjacent to the next channel, which changes it and allows it to open. And less more ions that influence the next. So it's just an adjacent type of physical thing that's going on. Notice how the sodium ions change the polarity locally, and now you'll see those potassium channels open up and potassium flows out. The reason it did that is because those sodium channels, those sodium ions, right, physically just change the local charge and change the shape of them. As well, notice how one area that was just reverses polarity, now it was depolarized, now it's repolarizing and hyperpolarizing, but the neighbor next to it is depolarizing. So it's just flowing and changing, right, quickly from one just microscopic area to another. That was really moving. And it just gets conducted, right, down the length of the axis. So this is what I was trying to explain on Monday and Tuesday when your eyes were rolling. Does that bring about any questions at this point about what an action potential is or the events that happen during an action potential? So I'll try to get through as much as we can regarding this, and some of it will be a review from last Monday and Tuesday. Question is, how does a nerve know that it's getting more of a stimulus or less of a stimulus? Nerve doesn't intelligently know anything, but one way that our body interprets how strong a stimulus is by how often an action potential is generated. Notice the word frequent. Frequent means what? Often, okay? Not the magnitude, not how high the action potential is, not the peak of it, but just how often an action potential is generated at a particular nerve cell. So this is, on the margin, be sure to write one way. We're going to add to this. This is the first one that This is one way that our brain, our central nervous system, can interpret a strong stimulus. So we're going to add to in chapter 10 and another factor that our brain and our central nervous system uses to determine a weak versus a stronger stimulus. Okay? One way is that action potentials are generated more frequently. So if a nerve cell generates action potentials, it's going to release neurotransmitter. If it's releasing neurotransmitter faster, that's implied as a stronger stimulus. Okay? So it's the frequency of the action potential, not the what? Not the what? Not the height, not the magnitude, not the degree of depolarization. Because it's going to depolarize about 100 millivolts. Okay. I mentioned a moment ago that there is a method to the hyperpolarization, and that's what we're going to address here. And it's this thing called the refractory period. This term is a general term. We'll use it to describe muscles. Okay, so we're not only using it in the nervous system, we'll use it in our muscles. You could use it in many other contexts. So in the nervous system, the refractory period is going to make sure that an action potential does go in one direction, so that it does go from the hillock to the terminal, and not, say, from the hillock to the dendrite. There's this control mechanism, if you will, in place to make sure the action potential goes in the correct direction. And it's called the refractory period. It can be subdivided into what's called the absolute and relative refractory period. And what I was describing earlier about the role of hyperpolarization is the relative refractory period. When a cell is hyperpolarizing, it's not only below rest, but it's also what? Really far away from threshold. Okay? And so what's the probability of a cell that's a membrane that's in the middle of hyperpolarization? What's the probability of it quickly switching to cross threshold? It's never say never in physiology, but it is extremely unlikely. Okay? And so it makes sure that once it generates an action potential, that membrane goes right back to what? Rest. So that it doesn't continue a period of excitation, that it doesn't need to be. So make sure it just goes through each step fully. Okay? Make sure it does its job. Okay? And so prior to that, when our sodium channels, after they depolarize, become what's called inactivated. So if they're inactivated, they're closed, they can't open, so they can't open, more sodium can't diffuse through them. So if we can't let more sodium in, we cannot continue to do it. We can't depolarize. We've got two protective mechanisms to make sure one action potential goes through all of the steps. Close those sodium gates, no more depolarization. Open the potassium gates really far away from threshold. And so if we were to quantitate it, honestly, you could shift this line a little bit more. Okay, but when those gated sodium channels shut, they can't let more sodium in. They can't continue to let more sodium in. So it ensures the continuation of the action potential. But really, we want to make sure instead of keeping it excited. You don't want to start a nerve excited and then just like stays positive 30 for like 3 minutes or something, just spewing neurotransmitters, spazzing out as you go. We want it to go back and reset, if you will. Okay. All right. And so figure 7.18 visualizes the role of the sodium and the potassium gates during that refractory period. Table 7.2 is going to compare and contrast a graded versus an action potential. We're talking in detail about an action potential today, and on Monday we'll get into the role of the graded potential. But it's imperative that you do go through those reading pages and get ahead into chapter 7 and 8, and obviously complete your homework. So it'll help a little bit. And I want to conclude really quick here. Shouldn't take us too long. And we'll summarize lab on Monday. We said the rate of action potential conduction is variable on two things. What? Size and myelin. Okay, so let's just conclude that. Point number 1. We said those cells that lack myelin operate via contiguous conduction. That's what you had to look up in your lab manual. And those that have myelin operate via saltatory conduction. As well, we learned that larger diameter nerves conduct faster. We'll conclude with just filling in those notes. On Monday, we'll pick up and talk in better detail about what myelin is. I just mentioned it in lab, so we'll give you some images. And then